if?
Yes, with an if. Yes, with an if. Okay, so we'll learn what the if is today, I guess. Okay, so our polar code's practical. As I said yesterday in the short talk, by practical I mean, can we build a chip that implements a decoder? Okay, and will this chip have good complexity and will be fast enough and all these things? So this is where we left off yesterday. Move this pointer away. Okay, that's where we left off yesterday. Polar codes can achieve capacity with two caveats. You have to use this successive-cancellation decoding algorithm. And this only happens as the block length gets really, really large. So what does this mean? Well, successive cancellation is really slow, and we'll see why. I'll go through the algorithm a little bit. It's bit by bit. You have to decode every bit in order, and this makes things really slow. The second problem is what happens at moderate code lengths. Well, the performance is worse than LDPC codes. That's what I mean by mediocre performance. Now, things do get really good if you have 1 million bits or more. Okay, so where were we when we started this work? We were looking at a situation of a decoder in hardware where you can get a few single-digit megabits per second. Too slow for any practical application. And what if you wanted to then have a really long code to get some performance back? You really couldn't do that because you couldn't build, imagine building an LDPC decoder with 1 million nodes. That would be impractical. So something had to be done. And I'll try to give you an overview of the progress towards practical hardware polar decoders. Okay, so we'll start off with a very brief introduction to channel polarization and polar codes. This here is the only equation in the entire talk right there, first and last. Okay, so imagine you want to transmit 2 bits over a channel W. So let's say I send a bit U0 over channel W, and I also send a bit U1 over the same channel W. And I receive noisy versions Y0 and Y1. Now, there's no reason to believe that you have any more information about U0 or U1 than the other. Okay, they're equally reliable. And this is the first and last inequality you'll see in the talk. Let's play a trick now. Instead of sending U0 and U1, let's send U1 over the channel and then the XOR of U0 and U1 over the channel. And now things are a little bit interesting because you see U1 appears in both Y0 and Y1. So we have just a little bit more information about U1 than we do about U0. Okay. So in a sense, you can think of having now 2 channels. One's a little bit better and the other one's a little bit worse than before. And you can keep doing this recursively and build bigger and bigger constructions for longer blocks. So here's one for 8 bits. And what will happen is that the different bit positions will polarize. Some will become a lot better and some will become a lot worse. And if you do this for very long block lengths, some of the bits will become so good that they're effectively perfect, and some will become so bad that they're effectively horrible and unreliable, and you can't transmit any information over those. So how do you build a polar code? Well, I find the k best positions, most reliable positions, and I stuff my data bits, k data bits, into those positions. So here would be 3, 5, 6, and 7. And then I say to the other positions are not very useful, so I'll just freeze them and put zeros on them. Okay, that's how you build a code out of this construction. And the interesting thing is, as the block length gets really, really long, the proportion of bit positions that are reliable is actually the channel capacity. Okay, so I want to look at decoding, and this is how successive cancellation decoding works. I want to explain to you why it's so slow. You're going to estimate the bits, given some soft information here, estimate the bits one at a time. So first I'll estimate 0, 1, and then 2, and then 3. And so the way this works is that estimates of previous bits get fed back into the decoder and then are used to estimate the next bit. So you can see, for example, let's fast forward to the process of finding estimate for bit 6. You see that there's inputs to this graph here are going to have the estimates for previous bits that are going to be needed to be known. So you have to do one bit at a time. Now, here's a snapshot at a point in time. I think there's actually a small mistake here, but anyway. No, there's no mistake here. Okay. You see that there's 2 kinds of decoding nodes, blue ones and green ones. Let's call the blue function f, because we're not very original, so we called it function f. It's basically a check node, if you're familiar with LDPC decoding, and has 2 inputs, soft inputs and a soft output. Now, once we get an estimate for bit 6, we can estimate bit 7. And here we're going to use, again, a soft input. And here we'll use all of this green function. We'll call this function g. And this is basically like a variable node in LWC decoding with one difference. So it's either an addition of this soft input or a subtraction of the soft input under the control of a bit which tells you to add or subtract. And that bit is going to be one of the previous estimates of the bits, or various partial sums of previously estimated bits. Okay, that's where the successive nature comes into this. Okay, so we looked at this and we noticed a couple of things. First of all, how many of these processing nodes, either these function f's or function g's, how many do you need? Well, it looks like there's n log n of them. Okay, that sounds like an awful lot, especially if you want to build a decoder with a million bits. So you can't really build 20 million processing nodes. It's impractical. Okay, so the first thing we realize is that you actually don't have to, because of the successive nature of this thing. The scheduling works out such that most of this tree is not doing this graph is really not computing anything at any given time. And so instead of n log n processing elements, you really need on the order of n. Okay, so that's an improvement. It's still not good because you still don't want to build a million processing elements. Okay. But when we looked at the schedule more carefully, we realized that if you look at, here's, let's say, a code for 1024 bits, and I really should be building on the order of, well, depends how you define processing elements, but we define it as you would need 512, so n over 2 processing elements to get the full decoding. What if we decide to use less than that number? What if we wanted to use a small fraction of that? Now, you can always do that. In LWC codes, you can always build a decoder with less than n variable nodes and n-k check nodes, but then you suffer some throughput loss. And so what we notice, though, in SC decoding is when you start reducing the number of processing elements, you don't actually see a corresponding decrease in throughput. And I'll explain why. So this blue curve is the utilization of my processing elements of my hardware. And okay, if I have only a very, very small number of PEs, they're heavily used. But as I add PEs very quickly, the utilization of the whole decoder goes down. Okay, so there's a lot of things that are sitting there idle doing nothing. So this suggests that I really don't need that many processing elements. So how many do I actually need? Well, let's define the maximum possible throughput you could get out of a decoder using n over 2 processing elements as 1. Okay, and then this red curve will tell you the fraction of that throughput you could get by using less than that number of processing elements. And we find for a 1K code, if you use, say, 64 processing elements, you get about 95% of the maximum possible throughput. So there's really no loss for building what we call a semi-parallel SC decoder. Now, the interesting thing, although I didn't graph it here, but we do have a graph, what happens when you scale n to be very large? Well, believe it or not, you get a curve that looks almost exactly the same. So for n equals a million bits, you need 64, 128, maybe 200 or so PEs, and you get almost all the throughput possible. Okay? So you don't need, the punchline is you don't need n over 2 on the order of n processing elements. You need a constant number of processing elements, and that constant is usually very small compared to the code length. So that was the first big result. Okay? And that resulted in an ASIC. This, we believe, is the first polar decoder chip for a code of length 1024 bits, rate 1/2. We did it in 180 nanometer CMOS, and I think the interesting number to look at is the throughput in terms of information bits per second was about 50 megabit per second. Okay, so this was done with 64 PEs. There are the PEs and circles in the chip, and the rest of the chip is memory. Okay. So the interesting thing about polar codes, it seems that you don't really need a lot of logic. Logic gates is pretty negligible. It's going to turns out most of a polar decoder is just memory. Okay. So then we asked the question, can you scale this up? And it turns out that last architecture you couldn't really scale. We didn't do something very efficiently, so we figured out how to fix that. And then we started looking at that new architecture, which is related to the last one. And we implemented this on FPGAs. And we see now we can scale up the code length up to about 1 million bits. And if we look at the numbers here, let's try to understand them. Lookup tables, you can think of this number as being proportional to the number of logic gates. Okay, so this is the logic, and then flip-flops and RAM are memory. Okay, and you see that the logic doesn't really change too much a little bit when you go up to very long lengths, but really very, very modest number of processing resources in terms of logic gates. And same thing with the flip-flops, it stays relatively constant. What does change, of course, is RAM. You need to store the metrics somewhere, and for very long input blocks, you need, of course, lots of RAM, but that's okay, that's expected. So this goes to show that a polar decoder is a bunch of memory and almost no logic whatsoever. So we can clock this at about 150 megahertz, which is okay for an FPGA. Things get a little congested when we get to very long lengths, so it drops a little bit, but not too much. And okay, we get about 50 megabit per second. Okay. So that's good. We answered the first question. Can you build a successive-cancellation decoder for million-bit polar codes? Yeah, you can. It fits on an FPGA, and it's fairly modest hardware. Okay, so this is a snapshot of where we were after that first generation of SC decoder hardware. So here we were about 50 megahertz per second. This is actually our original ASIC. If you were to implement it, the same architecture for rate of 0.9, a high rate code, you'd probably get about 80 or 90 megabit per second. And then, okay, Pamuk, who was one of Erican's students, had some nice tricks, and he got a similar kind of architecture up to about 100 megabits per second. So that's the snapshot of where we were after the first generation, 100 megabits per second, okay? And you could do long codes. Pretty good, but we want to do more. You know, from yesterday's talk, we could go to 100 gigabits per second. So where's the gap? So how do we get from 100 megabits per second to 100 gigs and get this 1,000 times throughput improvement? Okay, so to understand that, I think it's useful to view the graph as a tree. It's a different representation, and let's show you how to do that. So we'll take groups. So we'll start off at the left, the bits, we'll call those groups of 1, and then we'll start grouping groups of 2, and then 4, and then bigger as you go, okay? And let's start replacing these with some nodes. So here we have, in this case, this is a pretty cooked up polar code, but there are frozen bits here, and these are information bits, these three. Okay, so let's draw the frozen bits as white circles and the information bits as black circles. Now, if I have a node here that has two child nodes that are both white, we'll just color that one white. And same thing, if you have two black, we'll color that one black. And if you have a situation where it's mixed, then we'll color it gray. So you see we have now the next level of the tree, some white, black, and some mixed nodes here. And then we can keep doing that same rule until we get a tree that looks like this. And we're going to just use some thicker lines to indicate that as you get to the right of the tree towards the root, you're sending vectors of it instead of just single values, and you have these fat links. Okay, now let's turn this thing over on its side and look at the first thing we can do to improve the throughput, or decrease the latency of the SC decoding algorithm. And this is a nice idea from Almadar Yazdi and Shishang called Simplified Successive-Cancellation Decoding. And it's actually a very clever idea. Take a look at this subtree here. Okay, this subtree here consists of the bottom root, the leaves here, just frozen bits. So why should I have to, when I get to this point here, decode this tree successfully? First this one, then send information back here and send it back down there. I already know the answers. I know the answers here are frozen. Yeah?
I thought on the previous slide you said if there are two whites, you have a white top.
Yeah. This is maybe not following the same coloring rule as the last slide. That's right. I don't think it's important, but that's a good point. That's a great point.
So white is frozen, or?
White is frozen, okay? So why should you have to decode frozen bits? I know their value. They're going to be 0, okay? So just don't bother decoding them. And the same thing with these guys here. They're information bits. I don't have to decode them. Actually, there's a nice rule. I can just take a threshold and take the hard decisions there, okay? Now, it's very useful to think about this in a slightly different way. Think about this guy on the left as a rate 0 code, okay? And think about the just decoding, just replacing these values with zeros as a simplified decoder for that little rate 0 code that lives there. Okay, it's importantly a parallel decoder. The rule is I just put 2 zeros here instead of figuring out that's a 0 and then figuring that one's a 0 afterwards successively. Okay, the same thing with this rate 1 code. I can replace this with a simplified parallel decoder for this little rate 1 code. Okay, so I end up with a pruned tree where I do less successive cancellation and things are going to be faster. Okay, it's a very nice idea. So we took that idea and started improving it and going a little further. take a look at some other structures here. We notice that there are other codes that live inside this big polar code. So this left tree here is actually a repetition code. And the nice thing about repetition codes is we have nice parallel decoders for them. I mean, we have to restrict the size of the code that we identify. But if you do that, then you can completely remove successive cancellation from this part of the tree and replace it with a repetition decoder. And the same thing with this guy here. This is a nice example of a single parity check node code. And we have fast parallel algorithms to do decoding of those codes. And so what we end up with is a reduced problem where we have new kinds of nodes that have even new kinds of colors. So this green node is a repetition decoder, and this orange node is a single parity check decoder. And importantly, they're not successive. Okay, so we can do these. Sure, we do these fast. Okay, but we still do SC decoding there. So we have a reduced problem. I won't go into this, but we have all kinds of nodes that we can identify and replace with fast parallel decoders, repetition nodes, single parity check codes. We identify sometimes combinations when we have the combinations of both for limited code size. And also we just do ML decoding for some small subcodes in the tree. Okay, so we have actually a whole bunch of other ones as well. How does this work? Well, this is actually quite a small polar code of length 256. On the left, this is the prune tree after simplified SC decoding. And then you can see that you can identify these kinds of subcodes here. And this is the final tree we get with we call fast SSC decoding. So you do much less successive decoding than in the standard SC decoding algorithm. You'll see here that there's some half nodes here. This is actually some merging we do to improve memory access. I'm leaving all the details out, but it ends up being pretty optimal. Now, it's a pain to do this by hand, so we've actually developed a compiler to do this for us. So you put a polar code in, and it automatically goes through and optimizes it to find the best assignment of these nodes to minimize the latency. The other thing we do is we developed some generic hardware that can decode any polar code, and it looks kind of like a processor. It has some decoding elements which are going to implement these different decoder types. And what this compiler does is it outputs some instructions, a little program which your decoder runs to schedule the decoding of these nodes in the right order. So there was a question?
Do you have to pause and synchronize when you do these parallel decoding?
Yes, there's still successiveness going on here. This tree still defines as successive cancellation, but it's on a smaller tree. So yes, there has to be synchronization. And this compiler spits out the instructions in the right order to do things. So it's not completely parallel, but a lot of these sub-trees are computed in parallel.
And it does synchronization first, throughput?
Well, the successiveness still does hurt throughput, yeah. So how much? I mean, how fast can we make these things? So for high-rate codes, we have a decoder running on an FPGA. It'll decode any code of length 32K. Doesn't matter. You just put in different frozen bit locations. And long story short, for a very reasonable amount of hardware, at a clock at about 100 megahertz, you get the magic number of a gigabit per second. Okay. Now, how much of this is due to the original simplified algorithm and how much is due to the fast improvement to it? Well, we took our compiler and we just restricted it to only using the rate 0 and rate 1 optimizations and not using any of the other ones. And you get about 3 times the improvement. So about a 3 times improvement from SSC and then another 3 times from using the fast techniques. Okay, so here's a snapshot of where we were. We had 100 megabits per second, Pamuk's work, and then, fast SSC on an FPGA, about a gigabit per second, and then last year there was an ASIC at the VLSI Symposium, which actually implemented BP, which is about over 2 gigabits per second. Okay, so how do you situate these things? Well, first of all, they're for different code lanes. So this one's for 1K, this is for 32K. That might be a consideration. Megahertz per megahertz, I think the SSC decoder is actually faster. Okay, if you made this at 300 megahertz, which in an ASIC would be entirely reasonable, it would be faster. So, I mean, they're about the same. But I have a hunch that SSC decoding is actually more efficient than BP decoding, although there's still not enough data points to know that for sure. Okay, so how do we get down to 100 gigabits per second? So the idea is actually very simple. You unroll the tree and pipeline it. So here's an example for a very short polar code where we've already identified that there's some repetition codes and single parent check codes. So we put down some hardware to implement the different operations we're going to need. We're going to need some F and G functions for successive cancellation here. We're going to need repetition decoder, SPC decoder, and then some partial sum generators. And we can then pipeline the decoding of several code words through this thing as they come down. The information gets passed back up here, down to here, and back up to here, and the code words follow through. Okay. Now, there is a price for this. This is really, really inefficient. So we just did this to see how fast we could get. Lots of logic. So this is actually quite a big decoder. It does, interestingly, still fit on an FPGA. It's not completely impractical, but it's much, much bigger than our previous work. But it's also much, much faster. So it's 118 gigabits per second information throughput. So you'll see the paper, actually, we just submitted, has a coded throughput of 237 gigabits per second, which is pretty fast. And compared to the previous fastest work, it's orders of magnitude faster. But there is a complexity price to pay. So at least we now know that things can go fast. There's no limit to how fast this can go.
So you're pipelining multiple cohorts now, right?
Yes.
How many cohorts in simultaneously you decoded?
I don't remember actually how deep the pipeline is in this particular, but I can get you that information offline.
Get a speed up for about 100, right? So it must be about 100 code words at least.
I don't think it's that deep, actually. I don't think it's that deep, but we'll talk offline. Okay.
5 minutes.
Yeah. So I'll try to go really fast here. So one thing we noticed when we developed this was that our simulations ran really fast in software. So we started looking into this, and we realized that our hardware that we had built on FPGA looks like a processor. In fact, it looks like a modern processor. It has a very, very parallel processing unit with 128 processing elements that work in parallel and a bunch of memory. And that's pretty much what a modern SIMD processor looks like. And so we started realizing that this might be a good match for software-defined radio. If you look at software-defined radio, ECC actually is the second most intensive operation you need to do, so there's some motivation to speed it up. And what can you do with modern codes? Well, turbo codes and LDPC codes still you could only do recent results only a few megabits per second per core. Usually you're limited to one core because you have other things to do on the other cores. So we want to know, can you use polar codes to improve the throughput here? We were told that if you could get 50 megabits per second, that'd be something kind of interesting. So that's our goal. So long story short, we optimized our software. First pass through, we got about 150 megabits per second for different code lengths. Okay. Then we wrote a compiler to optimize it. Basically, what it does is it takes away all the branches and it does a bunch of other tricks to make the code vectorizable, so it can be mapped to SIMD processors. And this is all on a single core, on a Core i7, I think. And we have a few hundred megabits per second information bit throughput. So they're really fast. Okay, this is some latest work actually, which is just about to be submitted. There's a couple of different approaches to polar code in software. One approach is to decode a bunch of frames in parallel. So this is Legal and others took that approach. And we optimized the decoding of a single frame. You get about the same throughput, over a gigabit per second on a really fast processor, which is quite surprising that you can do that, but they're very fast. But the latency is much better, we think, doing it this way. So we have actually pretty good latency, about 20 microseconds, and very, very high throughput. And the comparison to LDPC codes in software is actually very favorable because you really can't do that many iterations of LDPC decoding because they're so slow. So then things start to equalize in terms of performance. I don't have the results to show, but you can see that since we can trade off performance and speed. Finally, I'll just briefly talk about improving the finite-length performance. If you want to make comparisons of bit per bit with LDPC codes, we saw that Tal and Vardy showed you how using a CRC and then list decoding, you can get the same bit error rate as LDPC codes. So what are the implications for implementation? Briefly, the way it works is you don't make a choice, hard choice at every step. So in the first step here, decoding bit 0, I know it's frozen, so fine, it's 0. But bit 1 could be a 0 or a 1, so why don't I go down both paths? And the tree keeps growing, but what I do is I prune the tree and I only keep the L best candidates, and so I have a list of size L. I use the CRC to choose from among the candidates on the list, and this actually was a huge improvement and very good performance. The problem is it's still very complex, so what does it look like to implement this thing? So we came up with an architecture. See, there's a bunch of decoders and memory, and we shuffle information back and forth. basically, it works for small list sizes. We can get, for code length 1K, about 100 megabits per second. So much slower than SSC decoding, but still somewhat practical. Finally, the last thing I'll talk about, because I only have about 2 minutes left, is what about software list decoders? So we know that list decoders are much slower than the Fast-SSC decoders we introduced, but they have much better error correction performance. So why not come up with a hybrid of the two? So that's what we did. First thing you should do is most code words are going to be decoded with Fast-SSC. So no problem, do that most of the time. If the CRC fails, then go to this list CRC decoder, which will be slower, but it should only happen very infrequently. Okay? So if you have a performance of Fast-SSC that's out here and the list CRC that's here, we actually implemented not quite the fast list CRC, but the SSC list CRC. We actually have a fast list CRC decoder now in the lab. It hasn't been published yet, but it will be very soon. And for length 2K, this is what the performance looks like relatively. But the throughput, what kind of throughput should you get from this hybrid system? Well, as long as you have signal-to-noise ratio that's high enough, you should get throughput that's approximately approaching that of Fast-SSC, but you should get the error correcting performance of the list decoder. So here are the results for what we call the two-step decoder. Using a list of size 32, we have a little bit of loss compared to an LWC code, which is in black. Using 64, size list 64, we can pretty much match the frame error rate of an LWC code of the same length and dimension. And then how about implementation and software on a Core i7? If you look at the information throughput in terms of megabits per second, the LWC decoder is pretty constant. It's pretty slow, a few megabits per second. But as I get to higher and higher SNRs, I really don't use the list decoder for the polar code very often, so my throughput just goes up really fast, and I can get above this magic number of 50 megabits per second. If I really want to match the LWC code, okay, I'm about 40 or something, but if I have a little bit of loss, I can get up to over 50. So this might show that there's some interest in software-defined radio for using polar codes. So in conclusion, polar codes can have excellent error correction performance. They also can have really good throughput in up to even the 100 gigabits per second range. So what we need to do now is to combine these two ideas. We have to combine the throughput improvements and the performance improvements. And once that's been done, we believe that this actually might be viable to use polar codes in much different applications.
Good questions, yeah?
I have a quick question. So the LDPC codes you were comparing against, this was the 802, the last slide you showed, this was the 802.3an Ethernet standard code?
Yes, that's the code, yes.
Do you remember what was the decoder, how it was implemented?
This black line here, this I believe, I have to check this, but I believe it's some kind of corrected min sum. Yeah.
For the LDPC code, do you stop the iterations as soon as the packet is decoded, or do you just run a fixed number of iterations? I'm surprised that the complexity stays constant as the SNR increases.
That's what I'm...
Right, that's probably for, oh no, it is actually for 30 maximum iterations, but it may stop earlier. Yeah.
Stop way earlier, given that your FER is 10 to the minus 8. On average, you stop much earlier. It's interesting.
How is it implemented, the LDPC decoder? So you just saw
So scaled min sum.
No, not the implementation, not the algorithm. Like, do you use the
Like a
MMX
fixed,
or SIMD instructions? You talked about using parallelism for the polar code. Are you also using parallelism for the LDPC?
No, I don't think it's vectorized.
You get a factor of 8 or so.
There's also the layer decoding architecture.
That's right. We didn't go into we didn't really optimize the LDPC decoder too much.
The next speaker will set up maybe one more. I know there's a lot of interest. Okay, but we have maybe one more last question, maybe.
Do you see much variation in the speed up depending on the actual polar code?
Yes. This tends to work better for higher rate polar codes. We haven't tried it for a variety of channels, just really AWGM channels.
Okay, so why don't you answer that question? But Mike will set up while you answer.
Just one question. Does it make sense to freeze extra bits or to choose special configurations so that your compilation will lead?
Yes, a good question. Can you change which bits you freeze to, and we have done this, and we see modest, maybe 8 to 10% speed up with no error rate loss by swapping some frozen bits and information bits around the border of reliable and not reliable to get better compilation. Yes, we've done that and it works.
Freezing extra bits, losing somewhat in the rate, but in order to gain.
We haven't tried that actually. That's a good idea.
No more questions? Okay. Thank you again.